And the next important discussion in our mathematical representation is parallel manipulators. So far we have seen these degrees of freedom for the serial manipulator, and now we will see the parallel manipulator. And first I will take the space robot, which is having a 3 degree of freedom. How to calculate this 3 degree of freedom we will see in a while. When we are dealing the kinematics, I will tell the procedure how to find the degrees of freedom for each and every robot here. So here this is the robot. See, this is the fixed base. Here this is the fixed base, and this is a moving platform, and this fixed base and the moving platform are connected with 3 legs. This is the leg 1, leg 2 and leg 3, and each leg is having the same type of joints and the links. Okay, for example, leg 1 is connected, let's say if I take the L1, in the L1, this is the fixed one is always considered the 0 link, and this one is the first link, and this is the second link. Okay, and this is the third link, or we can say that this is a moving link, link M. Okay, this is the link M. So here link 1 and 2 is connected with the prismatic joint, and link 0 and 1 is connected with a revolute joint. This is the revolute joint, and here link 2 and moving platform is connected with a spherical joint. So what is the spherical joint? It will allow the rotation about x-axis, y-axis and z-axis here, and all these 3 axes are meeting at one point. So x, y, z, all these are meeting at one point here. So that means here, if I can find out the center of the spherical joint, that means it is automatically lying on the corner, one of the corners of this moving platform. Okay, so here in the same way all the links are connected. In the same way all the links are connected. Here also revolute joint, on one more prismatic joint, and again here a spherical joint. Even here also revolute, prismatic, and then spherical joint. Okay, so here what is our ultimate aim? First of all, we need to ultimate aim is to find the position vector on this platform. Okay, so here what I try to do is I will find out position vector up to here, which is nothing but on the corner of the moving platform. So if I can find up to here, that is nothing but this portion I can find out based on its geometry. Okay, if I know from up to here, then from here I can find out based on the geometry. And here one more thing is, even though the rotation of the moving platform is happening with respect to the center, if I know the center, then I can easily travel up to here. Okay, so my main idea here is to find out the position vector up to here on the link 1, and up to here on the link 2, and up to this corner point on the link 3. So here what I do is I will choose the midpoint of this as the coordinate system for the base, and here let's say this is the x-axis. I will term it as a xb. Why? Because b refers for the stand for a base here. Okay, and then this is the yb, and then zb for example in this particular instance is going like this, zb. It may go through this, or may not go through it. Okay, based on its position, but at this particular position it is going through. Why? Because if I slightly tilt in some other direction, then it may not go through the geometrical center of this. Okay, so that is how I have taken, and I will assume that this is the equilateral triangle, the bottom one and also the top one. So bottom one is equilateral triangle, and this is at the centroid of the triangle, and this is passing through this revolute joint, and this revolute joint is perpendicular to the axis xb. Okay, so what I do is I will take one leg and I find out the DH parameters, and after that I will tell you how to find out DH parameter for the other links. Okay, so if you observe, in the previous cases when I am trying to find out the DH parameters, what we did, we adopted some laws. What is that? Whenever the fixed frame and the immediate nest link is connected with the revolute joint, then we have chosen the x0 or z0 and z1 at the same point. That means the fixed coordinate system and the first joint coordinate system are coincident. That is how we have chosen. But here I have already assigned one coordinate system to the base at the centroid here. Then in that case, what I need to do, I will assign again x0, y0, z0 here. Okay, and after finding out with respect to the x0 or z0, I will again transfer this base coordinate system to that. Okay, so what I'm trying to do is here, so first I will take one leg, this leg. So I have taken this leg. So this is the L1, this is the leg L1. So in the L1, this is the link 1 and this is the link 2, and this is the link 0. This is a fixed one and this is a link 0. That is how I consider a link base. I will say it is a base. Why? Because I assigned the coordinate system base here. So here, first we need to write down the joint axis. Okay, so if you take this is a perpendicular to this, but in 3D I have written for the sake of understanding. So this is the link 1, so this is the joint one, this is the joint one. Let's say this is the Z1, and where is the Z2? Z2 is connecting the link 1 and 2, and this is a prismatic joint. So the link Z2 axis is like this. Okay, this is the Z2 and these two are perpendicular to each other. And here we have 3 more revolute joint. The wrist is nothing but, the spherical joint is nothing but 3 mutually revolute joints. Okay, I will take one revolute joint here which is parallel to the Z1. Okay, this is also revolute joint, and here I will consider one of the revolute joints, and all these revolute joints are intersecting at the same point. Okay, and that point is lies on that moving platform. So I will take here one more revolute joint on this. Okay, this is passing through the center which is parallel to the bottom revolute joint. Then I will name it as a Z3. Okay, that is what I have done here, and I need to assign some fixed coordinate system. This is a base coordinate system, but we have been studying like whenever there is a revolute joint connection, then I need to assign the fixed coordinate system coincident with the first joint coordinate system. Okay, that means here I will choose one more coordinate system, that is a Z0. Okay, you forget about the base coordinate system. Okay, I forgot that this is my base coordinate system, but I am assigning here itself. Why? Because I know that how to translate. I will find out from here to here position vector and I can translate. Otherwise I can move this coordinate system from here to here, then I can multiply with the transformation matrix, so that I will get a position vector from here to here. You got the point? So what I am trying to do is I will find out a position vector from here to here, and I will transform this coordinate system to this, so that finally you will get a position vector of this point with respect to this. Okay, so here I will assign the Z0 here, and then I will see x0 is perpendicular to the Z0 and Z1. So something like this, this is a x0. Okay, and then x1 is here x1 is nothing but the perpendicular distance between the Z1 and Z2. This is a Z2 and this is a Z1, and this is the perpendicular distance. See, it is going like this. Okay, otherwise see, if you see, this is like this. This is the base, this is the Z1, okay, and this is the Z2. I am coming from Z1 to Z2. Okay, Z1 to Z2 like this. So see, this is the triangle, this is the triangle, and I have this here, and this is the Z2. So I am coming from Z1 to Z2. So how it is going? It is going outward. Okay, it is going along this xb, so this is the x1, and the angle between x0 and x1 is how much? Theta 1. This is the theta 1. And what is the x2? X2 is perpendicular distance between Z2 and Z3. Again, you know, these you need to remember, you need to by heart. Okay, Z2 and Z3. X2 is a perpendicular distance between Z2 and Z3, and here we have a Z2 and Z3. So if I draw, you know, this is the x2, this is x2, and the distance between x1 and x2 is nothing but a d1. Okay, I will consider this as a d1 from here to here. So I identified, see, if I see this in the 2D, then how it visible? See, this is the Z1, let's say this is the Z1. Okay, and this is connected to the another link, and again this is connected to the revolute joint, and this is the Z3, Z1 and Z3 parallel, and this is the Z2. Okay, so here this is a perpendicular, and again here also perpendicular. This is the perpendicular one is a Z1, and here also perpendicular one is a Z2. Okay, that is how it look like in the 2D. So now we need to find out DH parameters for this. So here DH parameters, how many links are there? So this is alpha minus 1 and a minus 1, and this is the di, this is the theta I. Okay, this is alpha I minus 1. So 1, 2, only 2 links are there. Okay, this is the 1 and this is 2. And what is the alpha I minus 1? Alpha I minus 1 is nothing but alpha I minus 1 is the angle between Z I minus 1 and Z I along about the x I minus 1. So if I substitute I equal to 1, then x0 is alpha naught is the angle between Z0 and Z1. Z1 and Z0 are coincident, so the angle between these two is 0, and when they are the distance between those two is again 0. And what is the di? Di is the angle between x0 and x1. Okay, so di is the angle between x I minus 1 and xi. So if I substitute I equal to 1, then x0 and x1. So first I will write the angle, that is the theta 1, angle between these two. Sorry, this is the not angle, this is the distance. Sorry. So theta I is the angle between x I minus 1 and xi. So the angle between these two is theta I, and di is the distance between these two. So distance between these two is 0. Why? Because those two are intersecting there. Okay, in the same way for the second, so from theta 1 to theta 2, when I am trying to go to Z1 to Z2, see, many times I am talking in terms of like instead of theta 1 I am saying Z1 sometimes. So but immediately I am correcting, even if sometimes by mistake, if I am not correcting myself, then by looking at the notation, you please note down that it is some trivial mistake from my side. So you understand. If it is conceptually wrong, then you please write us, but otherwise you please bear with us. Sometimes it happens, when you are continuously saying that theta, alpha, theta, z, x, then it may, something overlap sometimes. So the angle between here Z1 and Z2 is pi by 2, and when I am coming Z1 to Z2, it is showing the right direction of x1. So here it is a positive pi by 2, and these two are intersecting, Z1 and Z2, so the distance between these two is 0. And here di is nothing but the distance between in case of 2, it is the distance between x1 and x2, and the distance between x1 and x2 is nothing but d1. Okay, and here angle between theta 1 and angle between x1 and x2, see, with respect to x1 and x2 only distance is changing, but these are not rotating with respect to each other. When x2 is not rotating with respect to x1, then these two are always remain oriented in the same direction, but only the distance between them is changing. That means the angle between them is 0. That means both are remained oriented in the same direction. So here, if I find out transformation from 1 to 2, then I will get the position vector up to here, vector up to here. But finally I want to get a position vector from here to here. So what I do is, from base to t, I will do from base to 2. Base to 2 is nothing but b to 0, then 0 to 2. So b to 0 and 0 to 2. And here if you observe, this is the link 1. Instead of link 1, if I take the link 2, then again I will choose the coordinate system here as like in this case. What is the coordinate system? The z0, x0 will choose exactly like this, but only thing is the orientation of the base coordinate system with respect to that link 2 is changing. Okay, and even for the link 3 also we will choose the x0, z0 as like in the previous case. What I am trying to say is the DH parameters for all the 3 links is similar. I mean similar means the same thing we will get. Okay, instead of theta 1 we may get theta 2, instead of d1 you may get a d2. Okay, so for all the links we will get the same DH parameters. Okay, so here in that case, what is the meaning of this? So this particular matrix is same for all the links. Okay, so since it is the same for all the links, I will find out first that particular matrix. Okay, so first we need to find out the t0 to t. Okay, so that is nothing but t01 t and then 1 to t, 1 to 2t. So what is the 01? See here, and for the first link we have only 1 theta value and remaining are 0. That means here the rotation is about the z-axis. So when the rotation is about the z-axis, then it is a c1 minus s1 0 0 and then s1 c1 0 0 0 0 1 0 0 0 0 1. Okay, into here this is the second link. For the second link, if you observe, only there is one rotation and there is no rotation in the about the z axis. So whenever there exists only one rotation, then directly I can add the translation along the z axis into the the variables related to the x. Okay, but if you have a rotation here and as well as here also, then I cannot write it directly. Then in that case I need to write 2 transformation matrices and you multiply it. Otherwise you directly substitute in the original equation or matrix that we derived for the I minus 1 ti. Okay, so here the rotation about the x-axis, that is 1 0 0 and there is no translation distance here, so along the x-axis, so 0, so 0 0 and here cos 90 is the 0 and sin 90 is 1, so it is minus 1 and 0 1 0, here it is a d1. Okay, and 0 0 1. So finally by multiplying this you will get t 0 comma 2. t0 comma 2 is how much here? So this is a c1 s1 0 0 0 0 1 0 and here minus s1 minus c1 0 0 and here di means d1 s1 and then d1 c1 0 1. Okay, this is how we got this. So this is the So this is the same for each and every link. So in each and every link, only thing that we need to find out is find out the base rotation, base coordinate system rotation until it coincide with the Z0 and Z1, and then you multiply with this. So for example, if I take the link 1 here, link 1, then I need to find out the base coordinate system with respect to 0. So here what is happening, so for example here in this case, if I take here, this is the Z1 comma Z0, Z1 comma Z0. So finally this ZB come and coincide with this Z1 and Z0. So what I do is I will first translate along the x-axis, and I will choose this distance is a. Why? Because this is equilateral triangle. So I have chosen the value a, which is equal from here to here, and from origin to another revolute joint, and from here to here. Okay, so first I translate along the x-axis. Okay, translate along x-axis how much a distance, and after that I will rotate about x-axis how much, minus pi by 2. Why minus pi by 2? See here, I translated this origin from here to here, so this came here. So when it came, what happened? The YB is coincide with the Z1 and Z0, and ZB is perpendicular to the Z1 and Z0. So if I do rotation about the x-axis 90 degrees, then what happens? The ZB will come and align in the opposite direction of the Z1 and Z0. Okay, that is why I am doing here minus pi by 2. When I do minus pi by 2, instead of rotating in this direction, it will be rotated in the opposite direction, so that the ZB will go and coincide with the Z1 and Z0. Okay, that is what here I am doing. So when I do that, so we need to rotate that. Okay, so here, so I am combining these two. So first, because rotation and translation about the x-axis, so I can combine these two. So when there is a rotation about the x-axis, then it is 0 0, and it is a translation a, and here also 0 0 0, and here the value is 0, and here 1 and minus 1, 0 0 0, and here 0 0, and here 1. Okay, this is the value, and I need to multiply this with that. Okay, then finally I will get a b up to 2 for the link 1. So what is the value? If I multiply with this, that is a common vector for everything, common matrix for everything, then it will become C1 0 minus S1, and then this is a plus D1 S1. Okay, and again it is a 0 1 and my 0 0. Okay, and then here minus S1, and then 0 minus into minus plus C1, and the final one is here minus D1 C1. Okay, minus D1 C1, and the last row is 0 0 0 1. So here this is the value we got here finally. So here if you consider this is the final value. So here if you observe, the y value is 0. Why y value is 0? I chosen the coordinate system in such a way that here the y projection is 0 in this particular case. Okay, so that is why here y became 0 here in this particular case. Okay, this you note down, these values you note down. Okay, and again I want to find out for the link 2. So I found out for the link 1. Now I want to find out for the link 2. So here this transformation matrix is same, but only thing is this changes. Okay, so here what I do is first I will rotate about z how much 120 degrees. Okay, and then translate above along the x a, and then again rotate about x how much minus pi by 2. Okay, so what is the meaning of this? So here finally I should make sure that yb is coinciding with this particular coordinate, this z0 and z1. So for this revolute joint, this is the z0 and z1. So here if you observe, xp is perpendicular to the z1 and z0. So first of all you need to make sure that xp here will become perpendicular to the z0 and z1. Okay, so for that I will rotate this. I will rotate this frame like this. When I am rotating this about the z axis, then this axis should go and become perpendicular to this, and it is going from here to here. What is the angle between these two? The angle between these two is 120 degrees in the equilateral triangle. Okay, so I need to rotate about z axis of the frame xy 120 degrees. Okay, and again after that, the same operations we will carry out. What is that? Translating the coordinate axis of origin along this x-axis of a distance, and then you rotate the coordinate system negative minus pi by 2 about the x-axis. Okay, then finally the zv will coincide with the z0 or z1 there. So that is what we are doing here. So here in this case, then b0. So first see what I am doing here. I will combine these two. Okay, I will combine these two. First I am rotating and then translating. Okay, so rotating and I am translating 180 degrees. So 120 degrees. So this is a C120 and minus S120 degrees and 0. I will keep A. Either you can combine A in the below rotation or in the above rotation. Okay, S 120 degrees and C 120 degrees, 0 0 0 0 1 0 0 0 0 1. Okay, and then you multiply this with another rotation about the x-axis, that is the 1 0 0 0 0 0 0 here 1 0 minus 1 0 0 0 0 1. Okay, after multiplying these two, again you need to multiply with that. Okay, so the final answer, I will write down the final answer. I am not going to this is a link to, so this is a big 0 multiplied by 0 to 2. Okay, 0 to 2 is here, and you multiply these two and you find out that. I will write down the final answer, you compare with that. Okay, this is what the link 2, and for the link 3, okay, so if I take the link 3, then here for the link 2 I rotated 120 degrees. So what is the link 3? This is the link 3. So the x-axis which is perpendicular to this revolute joint should become perpendicular to this. Okay, that means it is rotating in the positive right hand thumb rule. So when you are rotating like this, then it should rotate how much? 120 plus 120, 240 degrees. Okay, so for the L3, first of all, about z-axis is 240 degrees rotation, and after that along the x, the translation is A, and along the x the rotation is pi by 2, minus pi by 2. Okay, minus pi by 2. So that is how we need to do that. That means to find out the B to 0 transformation for the link 3, instead of C120 you will substitute the C240. Here also S240, here S240, C240, and again here the matrix whichever we have written, this same will come. Okay, because here this is the x rotation about x minus 90 degrees, and you multiply these two, and again after that you use the same formula. You find out the B to O transformation, and then you multiply with the O to transformation using this. Okay, so finally you will compare with the answers that I am going to write here. So finally these are the vectors. Okay, this is the link 2, and this is for the link 3, and what is the position vector here? This is the position vector for this, and this is the position vector for this. Okay, the x, y, z value and x, y, z values. So what is the meaning of that? So this is the x, y, z value with respect to the base B. Okay, this is the OB with respect to the OB, and this is the, let's say this is the S3, this is the S2, and this is the S1. Why I am calling S? This is spherical, so the center of this is represented as a S1, S2, S3. Okay, and here one more thing you need to observe is how to measure the theta 1 here. Theta 1, theta 2, theta 3, how we are measuring, that we need to again see. So what is the theta 1? If I take the link 1, what is the theta 1? Theta 1 is the angle between the x0 and x1. Okay, for example, if I see this in the front view, the base will be like this. This is the base here, and this is the base will be visible as a line here. Okay, so here this is the x0, and this x0 is always constant. Why? Because this is a fixed coordinate system. And where is the x1? For example, this is the link 1, and here this is the z2, and this is the this here perpendicular to this is z1. The intersection is x1. The intersection is x1. So here in this particular case, when it is 90 degrees, x1 and x0 are coinciding. So instead of that, if the link is like this, then this is the z2 and this is the z1, and the x1 will be like this. Okay, x1 will be like this. So here in this case, this is the theta 1, and if the link is like this, then this is the x1, and the angle is this much. Okay, so here always we are measuring the angle with respect to the x0 to the x1. That you need to remember. In some of the examples, for example, we derived everything in the symbolic format. In the examination, if they ask you to find out symbolic format, and at the end if they ask you to substitute the values, in that case, instead of giving the angle from the outside, if the angle is given between the link and the base like this, something like a 60 degrees, then how much you need to substitute, that you should be very much aware. If you substitute 60, then you will get the wrong answer. Okay, how much you need to substitute? You need to substitute 180 minus 60, theta equal to. Why? Because we have chosen the theta from this direction, from the x0. Okay, so that you need to observe here. These type of things, even though looks simple, you may neglect blindly, and you see deriving all this is not so easy. Marking the coordinate system, writing DH parameter, you are doing all the great work, but at the end if you make a mistake in the simple thing, then all our effort will be ruined. So you should be very careful about this. So how we are choosing the theta 1, how we are using the theta 2. Okay, these rotations you should be able to visualize and measure properly. Okay, and here one more thing I would like to emphasize. Anyway, we are going to see this in the kinetics of the robotics, but again I will emphasize here. This is a 3 degrees of freedom space robot. So here they said it is a 3 degree of freedom. That means only 3 input. 3 inputs mean 3 3 joints will be activated, 3 activated, and remaining will not be activated. What is activated? We will give some external power to it. Okay, so that means here we have how many joints here? 3 rotary, and then 3 prismatic, and 3 spherical. But here we are activating only these 3 prismatic activating, and remaining are passive joints. These 3 revolute and 3 spherical, these are passive joints. This you need to observe. But in the serial manipulator, we didn't find this type of situation, but in the parallel manipulator, we will find such type of situation. Okay.